Okay? Good. So I'm taking part in development Python itself. My last passion for last years is asynchronous programming. Don't know, maybe async.io library, and HTTP is both client and server for async.io. And I'm working in Ocean SA company. The company analyzes a lot of texts from internet. So we should deal with different encodings, with Chinese pages, Arabic pages, whatever. And we learn many lessons from it. So, very short historical recall. At very beginning was ASCII. ASCII is 7 bits characters. 7 bits means you could put into numbers, letters, English letters only, and some punctuations, nothing more. But I am Russian. We use Russian texts. And ASCII could be extended to utilize high bit and get 128 characters for Russian letters. But the problem is at least six different encodings for Russian. And these encodings are not compatible with each other. So you should know what encoding is to interpret, to read the text. And moreover, if you use Russian, you cannot put in the same file, in the same text, say Japanese, because no space for both Japanese hieroglyphs and Russian letters. That's why Unicode travels funny glyphs, by the way. Unicode is technically 4 bytes internally. Not all bits from 4 bytes are utilized. It has only 1 million code points. Code points is a terminology for symbols in Unicode. Supports very many languages, historical scripts, hieroglyphs, ideographics, emojis, whatever. Everything is in Unicode. And if some glyphs is missing, Unicode is extendable format, and we have very many space for put everything. But code points, you should remember it. Code points is for in-memory representation. It's a logical number corresponding to symbol, but not data representation used for storage. If you get a file, get a page from internet, you get it in encoded form, and you should convert it into Unicode. How to do it? Codex. Codex is a really big black hole. Let's talk about UTF. Everybody knows what UTF is, but mostly what is UTF-8. UTF is a binary representation for storing Unicode, reading and saving. So in Python, Unicode is for string types, but if you put bytes on disk, you should use bytes, convert to Unicode. For files, network, database, whatever. And other codecs, like mentioned above, Russian codecs are also binary representation, but Russian only codecs are limited, I told about. You cannot use other symbols. But UTF is not so simple. You see, 5 UTF kinds, and also you can multiply everything by bomb. I'll tell you about what is it a bit later. Let's start from simplest one, UTF-8. My members. UTF-8 is for saving everything again. And UTF is a compact transformation. It means it uses as many bytes as possible for symbol. So if symbol contains only ASCII before 1 bit, it's saved as 1 byte. But for Russian, UTF-8 uses 2 bytes with first byte and second byte. And so on, so far, this range is used mostly for some kind of, Chinese symbols, and last set is for modern additions, latest additions. So you should remember, UTF-8 is for saving all available symbols. But also exists UTF-32. UTF-32 is pretty simple. It's just saving bytes, code points as is. But there are 2 kinds. One is low Indian, second one is big Indian, little Indian, big Indian, actually. What's the difference? In a machine, you can put bytes starting from lowest one and from highest one. It's different mirrored representation. And you should know what kind of endian is used by file. Otherwise, you'll get broken text, obviously. So, 2 kinds, little and big. And UTF-32 is not so widely used as UTF-8 because it's not so dense. It uses more bytes usually. It will use 4 bytes per character, even 4 ASCII characters. UTF-8 is better. But also exists UTF-16. Why is it exist? For historical reasons, mostly. At very early ages, when people figured out that 1 byte is not enough, they said 2 bytes may be good enough for everything. And with these assumptions, Java strings was built, Unix internal strings was built, and this assumption obviously is wrong. So in Java we have 2 bytes, 1 word per character for 1 codec point, but it does cover the whole Unicode range. So symbols in this, symbols with code points more than 10,000 are encoded as 2 bytes. It's called surrogate pair. Surrogate pair is first byte in this range and second byte in this range. So this is just a small example how to convert large symbol into surrogate pair. In practice, it means you can get surrogate pairs in UTF-8, even in UTF-8. It's forbidden by definition, by standard, but world is not perfect, so some pages can have surrogate pairs. Unfortunately, you can ignore it, you can translate it. It's not allowed, again, by UTF-8 strict version, but allowed by non-strict. And again, UTF-8 could be Little Indian and Big Indian, because 2 bytes could be flipped depending on machine configuration. So, what is bomb? It's not successful attempt to provide information about what UTF encoding should be used. At very beginning of the file could be garbage like this. The bytes defines what encoding is. Most internet pages, most internet data files and so on does use BOM. But in Windows, if people edit file with Notepad, Notepad tends to add BOM prefix. So if you get file with from untrusted source, you probably should check if it BOM prefixed. No? Okay, let's try to use it as what? Interesting question, because you don't know what encoding is for file, except if it's provided by content type header or specified by other source. So BOM tries help, but it's mostly ignored. This is reality. How to check actual encoding? You should try. There is a library, say, called chartdet, which tries to sniff several kilobytes from text and apply different encoding. And the tool reports what encoding is most fit, better fit to text. But it's not guarantee, again. Now we are moving to actual encoding problems. When you decode bytes trying to get string from UTF-8 encoding without parameters, with strict default error handler, you'll get exception if the text is not UTF-8 encoded. There are many different error modes mentioned here. It's just standard Python documentation. And most useful are 3. Ignore. Just drop all characters which are not recognized by specified codec. Maybe it's an option, maybe not. For us, we are trying to analyze text, and if we cannot recognize character, this character does exist for us. So ignore option is safe for our job. Replace option replaces non-decodable bytes with question mark. It's just sign that something was wrong, but text at least present, at least something you can read, but maybe partial information is missed. Backslash replace keeps non-decodable bytes as backslash x and hexadecimal representation. What to choose depends on you, but you know, if you cannot decode a text as UTF-8 while the text is actually almost fully compatible, you can use different error handlers. So, composites. This is more important thing. String love, lion in Germany. What do you think? Strings are equal? Not actually not always, because strings have different length, and the problem is in letter. Why? Because it could be encoded into one character with this code. Oh, sorry, should be another number, and into two characters with lowercase ASCII O and a special character for two dots. It's called composition. One symbol could have many different representations. Why? Because Unicode is not only for storing, but for displaying and printing also. So it's impossible, almost impossible, to make a font with whole Unicode range. Much easier to make a font with O letter and two dots, and compose these representations on printing. But if you analyze text, you should have some normalized form. That's why Unicode data is standard model, exists. And the model has normalized function. First parameter is form, second is string, and available 4 forms. Composed forms, normal form, composed. All composites are joined. This form is decomposed back. All symbols which could be split into composites should be split, and they are split after return from the function. These two forms are tricky because one symbol, say Latin number, like 1 is I, 2 is 2I, and so on. This Latin numbers has own code points, but could be converted into just ASCII. And key letter means everything in argument at first decomposed, so characters like Latin numbers are converted into ASCII numbers, and after that they are composed or decomposed. What form should you use? I don't know. It's up to you. But you should normalize all texts before making comparison to avoid cases like lion is not lion. This example. Here, actually, parameter could be in any form. Composite, decomposite, doesn't matter. Normalization into composite form always return 4 code points. Normalization into decomposed form returns 5. And that's what you should know about Unicode normalization. Unicode categories. It's interesting thing because in Unicode all characters, all code points split into many categories. Examples are category for space is separator, that character is used. Separator, space. Category for Arabic number 1 is numeric digit. This is letter uppercase. You can get a category for everything. And why is it important? Because, sorry? No. Because we say want split into spaces. We want to extract words from text. And in Unicode the standard, there are many spaces and many punctuation. You cannot enumerate everything, but you can use categories. And every symbol in Unicode code base has name. You can get name and you can construct from name again. Python supports it out of the box. Returning to spaces. Let's see. In Unicode, there is 17 space symbols and 700 punctuation symbols. It's very huge amount. And if you see in code like split by spaces, where spaces are space, tabulation symbol, new line, whatever, most likely the code does work with Unicode. Sometimes yes, sometimes no, it depends on incoming text. So, what spaces are? This is a list of 17 spaces. I have no idea about very many of them. So sorry. Maybe the spaces are very important on text representation. There are spaces which should be not. The space does allow line break between words. It's typographic thing, may be very important, very cool, but it's different space. Thin space, thick space, hair space, whatever, I don't know. Yeah, but very many spaces and even much more punctuation symbols, not only dot, comma, and question, exclamation. So you should analyze text in more smart way. One of very widely used tool is regular expression, at least for text pre-processing. Our artificial intelligence team use smart, complicated models, neural networks, whatever. But at first step, they prepare and comment data. Use tokenizers, extract words, normalize words, and so on. And this task is based on all good regular expressions. And there is a regex library. The library is pretty old. It's written and supported by Python core developer. And the library has more rich interface than standard re in Python. Why regex did not replace standard re yet? The reason is standard regex library is good enough for very many use cases. But if you need some smart analyzing, most likely you need more powerful regex library. It's installed from PyPy, available by PEEP, and regex supports things like this is any character from this category. So splitting by spaces and punctuations. It could split into words everything. You should remember about categories, remember about non-ASCII characters when you analyze text. Last thing. We are living in internet age. So we usually dealing with URLs, internet addresses every day. And internet has own encoding. The encoding is basically it is UTF-8. But symbols, this is a Russian symbol for key, is encoded as percent to hex digits and next percent and 2 digits. Actually, it's UTF and 8 encoded in 2 bytes for this Russian text. And this part of path is encoded into non-pretty looking but working UTF-8 percent encoding string. And this format is what actually should be passed through network. Browsers do it. Web servers accept percent encoded strings. By the way, this library is used for converting, constructing URL object from everything and converting it implicitly into network format. So, and person encoding is for everything except DNS. Domain name could be in Chinese, in Russian, written in Arabic script. It's a relatively new addition. Many people hate it, but it exists and we should work with it. And there is a encoding called IDNA just for domain names. IDNA encoded text contains only ASCII. It's prefixed with XN dash prefix. And why do we need it? Because in the world, very many old designed switches, network communication equipment, which know nothing about Unicode. But if we convert all DNS names into something like ASCII, this equipment will continue working without any change. So internally, everywhere, A labels, A for ASCII, U for Unicode. In certificates, sites are signed by the A label form. And funny Bach, Python currently does support it. There is a fix it will be applied to Python 3.7, but I think I has problem with fetching HTTPS sites like this.
They don't support underscore and now they are supported.
Underscore?
The underscore character
Yeah.
don't support DNS and now they are supporting.
Again, in IOLibs, there is a tiny library for monkey patching hostname check, but it's backward incompatible change, and it could be fixed only in 3.7 to don't break everything in 3.6. It's already broken, but sorry, sorry for that. So that's it. Questions? I suggest using chardet or C chardet, accelerated chardet, to feed beginning of text and figure out what encoded is. Because encoding information in content type is not reliable. In very many times it's broken. And what we are doing, we are trying to at first figure out encoding from content type header. Then we do probe if codec throws an error. We are trying to use chardet and encode again. If it's still broken, okay, let's do UTF-8 encoding with replacement mark, and it's the best what can we do. No good solution for broken data, sorry. Done. Thank you.